Thank you very much indeed, Brian, for your kind introduction. And it is a pleasure to be here, and a particular pleasure with you as my chair, long-time colleague and friend. I'm starting by asking a question: can we do better? This was really driven by the topic of the conference, inspiring the next generation. When I was asked to give this lecture, I didn't know that topic. But in thinking about what I wanted to talk about, the word inspiring and the idea of inspiration of the next generation is something which is very close to my heart. And as you hear, I'm a visiting professor at Warwick, so I'm involved in education as well. But can we do better is the question. Inspiration is a vitally important part of what we do. You know, the stuff that goes into my brain, your brain, is a mixture of stuff, and we use our imagination to kind of make sense of it all in order to generate ideas. But broadly speaking, you know, it's information, the stuff that we learn, we research, we experience, all the important knowledge that we gain through our careers, that allows us to do the engineering that we do. But without inspiration, it comes to nothing. We need inspiration. So I was delighted to see that topic. And I asked myself, where do we get inspiration from? Of course, we get inspiration from people. And I just, you know, I could list a long list of people. Here's Christian Menn with his wonderful Sonneberg Bridge in Switzerland. You know, Joch Schleich is somebody who has been a great inspiration to me. And of course, his son, Mike Schleich, the firm in their names, like Bergman and Partner, you know, continue to inspire people all around the world with the work that they do. And we look, don't we, at our at colleagues around the world, Michel Villager with this sublime Millau Viaduct in south of France, and other things as well, of course, and bring it up to date, more up to date with Laurent Ney. And this is the Tintagel footbridge, which is certainly worth a pilgrimage to go and see it. But I mean, and I could name literally hundreds of people who have been an inspiration, and I would hope that many of you listening would also be able to talk about people who have inspired you. But we also get a lot of inspiration from history. And here is something which is over 2,000 years old, which has been standing there, built by the Romans, using local materials, you know, using a very basic, simple structural form. And there are countless numbers of similar structures, not as old, but similar structures around the world, which last, which stand the test of time, using local materials responsibly. And you'll see where I'm leading, perhaps, with my talking already. We could come a little bit more up to date with iron. In England, in the 18th century, Iron Bridge here, of course, and you know, spectacular bits of metal bridges, and one of my great favourites, the Pont des Arts in Paris. So we get inspiration from these, and of course, this bridge is a source of inspiration for countless lovers, you know, couples who go there to pledge undying love, and they attach a padlock to the parapet. At least they did until it was stopped, because the padlock was in danger of the parapet was in danger of collapsing under the extra weight. But you know, these things could be inspirations for others as well as ourselves. The age of steel, of course, arrived at the end of the 19th century, and then we into reinforced concrete and the sublime work of Maillard, Robert Maillard in Switzerland, and you know, things like this, the post-tension concrete structures that started to evolve, and you know, all of this in my world, the bridge world that I've been inhabiting for the last whatever it is, 40-something years, is where inspiration comes from. And bridge design, bridges we have to design for a design life of 120 years, generally speaking, which is interesting. When we look at the sort of history, the perspective, and there was that bridge 2,000 years old, but we're designing for a 120-year design life, and there's all sorts of reasons for that, which I won't go into. And now, in fact, we're being asked on a number of occasions on the bigger bridges to design for 200 and sometimes even more. And just that thought let me think about an inspiration from Captain Samuel Brown, who designed the fabulous Union Chain Bridge on the border between England and Scotland, which is almost exactly 200 years old. It is actually currently going through some renovation, I'm glad to say, but it still carries traffic 200 years later. And the astonishing thing to think about is that when, at the time he was designing it for things like this. Actually, I looked at this photograph again this morning and realized this actually is about 100 years later than the bridge, because in the picture behind the chariot, the carriage here, there's reference to electric something. So it certainly wasn't. This picture does not date from Samuel Brown's day. But you can imagine that he had no idea about what was coming. This kind of thing was unimaginable 200 years ago. So do we kid ourselves when we say that we're designing for 200 years? We have absolutely no idea what we're designing for. We just don't know. We don't know what we're designing with, what materials we'll be using. If we design something today for today's conditions, we need to be thinking very, very carefully about how is it going to last. Going back to the beginning again, this idea of inspiration. If I, in my little tiny career, have been able to inspire anybody, it would be to say, how do we ensure a future? Can we do better next time? Because I absolutely have to say that there are also a lot of things that I would certainly not do the same way again next time if I had a next time. And we're into the age now of 3D printing. This is the bridge in Amsterdam, which has finally been installed after a lot of waiting. 3D printed steel. We'll probably be talking about flying cars. We've already got autonomous electric vehicles and that sort of stuff, which were unimaginable even just a few decades ago. These things will be coming, and goodness knows how we'll be traveling around in the future. And so are we aiming at some kind of ghastly future city, future environment, which is the sort of stuff of science fiction? And what are the implications of that? Or are we possibly looking at a future city in 100 years' time, 200 years' time? Here is an illustration which I've used before, but it's not mine. But it's an illustration of a green city. And so I have to ask myself, what about the future? And I don't know about you, but for me, I had a very, very abrupt wake-up call about 2 years ago. In the summer of 2019, I saw this chart, for which I give credit to Will Arnold at the Institution of Structural Engineering. I hope it's clearer on your screen than it is on mine. I'm sorry, as I'm looking at here, it's all rather blurred. But what this is showing is energy-related carbon dioxide emissions per sector, and the large blue slice is buildings. 39%. 39% is due to buildings, transport and other industry, and the other three slices. The biggest part, by a long way, of energy-related CO2 emissions is due to buildings. That's the stuff that you and I are involved in, all right? Building structures. And if we break that down further, then, and again, I do hope you can read this, superstructure is the largest bit. Now, the audience or the delegates for an IASS conference are largely people who deal with superstructure. So the awakening for me in the summer of 2019 was that structural engineers are playing a very big part in creating the biggest problem currently facing the planet. I'll say it again. Structural engineers are playing a very big part in creating the biggest problem currently facing the planet. It's not something that is dealt with by aviation or the food industry or clothing or manufacturing or any of that stuff. It's structural engineering. It's building structures. It's the stuff that we do. It's the biggest part. And right now, certainly 2 years ago, our professional institutions and associations didn't require us to do anything about it. Now that's changing, I'm very glad to say, because I think not only I, but many others had that wake-up call. That alarm went off in the summer of 2019. It was too late, but it's at least gone off. What we need is a sort of Hippocratic oath. This is, rather like doctors do have. that actually what we need to be doing is making sure that the way we perform is responsible in this field. This actually comes from the New York State Professional Engineers Creed, which they have to pledge, and in the middle of this it talks about human welfare, public welfare being the most important element of what they're doing. And of course, that's true, and indeed our own codes of conduct have that. But I do think that we've got a way to go before we, all of us as professionals, realise the seriousness of the issue that we are having now to address. Thankfully, last summer, 2019, that was taken up, and you will know. I hope you know about this. So the UK Structural Engineers Declaration, the Institution of Structural Engineers, set this up, in fact, following the lead from the Royal Institute of British Architects. And now, around the world, this has been picked up. The declaration about climate change and biodiversity, the emergency that we face. And I haven't got time to go into all the things. What I would urge you to do, or every one of you listening to me today, if you don't know what this declaration says, and if you haven't yet signed up to it, please would you go to Engineers Declare or Construction Declares, or just Google that and it'll come straight up, and learn, educate yourself about these things. We all need to sign up to the things that this is about. So there's my soapbox over. But the Institute of Structural Engineers, I would say, is really leading the way in this. And Will Arnold, I've mentioned before, Mike Cook, who you will know, I'm sure, he's probably speaking in this conference, is leading the effort. So I take no credit for it, other than just being a bit of a flag bearer. Please do check out what the resources are there, because they help. The Carbon Tool, the resources are there to help us. We've all seen charts like this. We've all seen these pictures which show the carbon emissions growing since pre-industrial era. This sort of long flat line, which then come the 19th and 20th century begins to grow, and then growing ever faster. And again, I look back at the title of this conference, and we're talking about inspiring the next generation. And the inference of that is that the previous generation, my generation, has got something worth inspiring. Okay, inspiring the next generation. But if you look at the last 30 or 40 years, I'm not sure that we can really hold our head very high if we're responsible for the biggest part of this. And you could see other charts. This is exactly the same figure, but showing it broken down. I can't read it on my screen at all. It's very, very clear when I see this normally on my PowerPoint, so I hope you can see it. But what it is showing, in fact, is by country. And a large number of the countries, actually, for the last 10 or 15 years, the numbers, the bottom, the lower curves, they're all turning down, which is fabulous. So, many countries around the world are beginning to address this problem. China and others, unfortunately, are not yet. So there's a really big issue, and we, each of us, need to do what we can, even though many people are saying, "Oh, it's such a big problem, we can't possibly do anything ourselves. What can I do when it's such a big problem?" That, of course, is thinking that leads to disaster. We all of us need to do something. And of course, we could do it in a small way. You can cancel that flight to New York, save a ton. You could go vegan and save a couple of tons. I'd rather keep my beefsteak. You can give up the car. I've gone a little way towards this because I've now got electric cars, but that's, unfortunately, I charge my car from the mains, which is still driven predominantly by fossil fuel. Not until my electricity supply to my house is a responsible supply from renewables will it be genuinely good thing to go electric. But here's the thing. We could design our building structures 20% more efficiently. That actually is really quite easy when you start thinking about it, if you look into what we could do. This is based on the 200 tons a year is based on a structural engineer designing. I can just read this, I hope you can, 40,000 square meters of new buildings a year, which is quite typical, with a typical carbon footprint of about 250 kilograms per square meter. This is quite typical sort of numbers. So you'd be responsible. If you're doing that, you're responsible for 1,000 tons of carbon a year. So design 20% more efficiently, you can save 200. in the bridges world, which is the one I inhabit, it's actually a little bit more difficult, I think, to design take 20% out. We're already designing to a minimum weight. We have to, because weight, the penalty on weight is that much more significant on very long spans. It's very challenging. But let's say I could design 10% more efficiently, and of course I could if I put my finger, really worked hard, and that's based on some new figures down the bottom. So again, the message is that we have the opportunity. Not only are we a big part of the problem, but we have a big part of the solution in our control. We can do something about it. So you all know about the 3 R's: the reduce, reuse, recycle. And reducing is to go lightweight and to use a little minimum amount of material. Reusing is interesting. Reusing is very interesting because we're seeing components, modularizations happening, beginning to think about how we can design our structures that are components that can just be reused. It challenges us to think in those ways. Recycling, of course, we're already doing quite a lot of that. We could do more. But let's go back to that figure. This is the same sort of figure, but with a different scale. I've just got the last 60 years on it now. Okay, so there's those big charts we were looking at earlier on, and you probably can't read that. I can't hardly on my original. I probably have to pick it up. But those three points are the Rio conference, the Kyoto conference, and the Paris conference. Those accords, which seem to have made absolutely no difference really to the incessant upward curve. But the challenging thing is that we've got to go to zero by 2050. Several countries, ourselves included, UK included, have signed up to achieving a zero carbon economy by 2050. But just look at that. I mean, that is it's an impossible. It looks impossible, doesn't it? It's a very, very significant about face. If we all start doing our 20% and our 10%, we might be able to begin to sort of make some slight improvements, and that's what we call a sort of business as usual improvement. That's the kind of curve that we could envisage that, couldn't you? You could imagine that, turning the curve downwards. But to get to this requires some very, very radical change indeed. And I think if you see that same thing on the earlier charts, this sort of thing, it just doesn't look likely, does it? And as we already know from the IPCC report, which was published a few weeks ago, they don't think so either, and the scenarios that they have published are frightening indeed. So, and like I remind you again that we structural engineers are responsible for a very large part of the problem, all right? But we are also able to think about the solution. So, in terms of inspiring the next generation, I'm thinking that the next generation is going to be inspiring us. So we should be doing more. We should be refusing to build new things, and that's already happening. And we could certainly be regenerating using much better use of existing structures. And we all know, of course, that the best time to influence the decision is right at the beginning, when we could actually influence the brief, because later on you could tinker with the details, but you're not going to really make much impact. My early career, I started with Flint Neill, as you heard, and relatively early in my career, I was working on the strengthening of the Severn Crossing. A wonderful project to be doing. And of course, back then in the 1980s, I always like to show the picture from this side because I was working on the Y bridge, this bit down in the foreground. But back then in the 1980s, nobody was talking about climate change. Nobody was talking about carbon. But nevertheless, the same principles apply to keep the asset open, to do the strengthening, to do the minimum necessary to give it a new lease of life. Brian, you might remember the numbers, but I think we added a few percent to the weight of the bridge in additional stiffening and so on, and increased the live load capacity by, I don't know, 100% or something. I don't remember what it was, but it was a massive change. That is the sort of thing we're supposed to be doing, making use of existing infrastructure and so on. I'm just going to go a bit more quickly here because time is running short. This is a bridge I did quite recently, a new bridge where, clearly by this stage, 2018, I haven't yet had my wake-up moment, but clearly designing lightweight was important, and we were able to achieve that here with a very, very light and slender arch, using those those ribs, those sort of outriggers acting to stabilize the arch, so it can be really, really light and thin. A delightful little footbridge. But you could start using. We do need to start using timber more. This is by Miebach, not nothing to do with my work, but just as an example of timber and concrete in composite action. This is something we'll be seeing more of. Stone, wonderful work of Webb Yates and the Stonemason Company, use post-tension stone. That staircase on the right really does stack up. The stone blocks post-tension together. Photograph taken before the balustrade was put in, just to demonstrate that it does work. And we'll be seeing much more of that. I'm absolutely convinced of it. These are little stone bridges. Really, really beautiful post-tension stone again, by Kuthler, a company worth looking into if you're interested in this kind of thing. Very, very slender footbridges. This is designed for a 20-ton vehicle. And it's just stone, slabs of stone cut and pre-stressed together. Going back to that stone arch that I showed you, 2,000 years old, we're going to see more of this going on. People using local stone, local material, looking at the carbon in the structure, not using massive industrial process to produce concrete. Why take a block of stone out of the ground, which has got a strength of, I don't know, 300 megapascals or something, and then you crush it and process it and use a whole lot of energy in order to produce a block of concrete which has got a fraction of the strength. It makes absolutely no sense at all. This is a beautiful stress ribbon bridge, a granite bridge from Schleichbergman, of course. This is an interesting material. This is something I recommend you to look into. Biomason. This is just a startup. These are biofabricated masonry blocks with a similar strength to concrete ones. These are mycelium. This is bacteria grown locally on site. Carbon negative. There are lots of people doing things like that. I'm having difficulty reading these slides. I don't know. I really hope you are not. But these are infrastructure is a very different thing. I just want to finish with this really, because infrastructure is different to buildings. To build less is obviously a useful guide in both cases, but sometimes in the case of infrastructure, it can be the wrong solution. We need to be building responsible infrastructure, of course, but we need to be building nuclear power stations and wind farms and all the tidal energy things and so on that we can be doing. And in the bridge world, of course, we need to build lightweight. But bridges are essential, for the societal needs. And as we know, capital carbon, i.e. embodied carbon, capital carbon is less of an issue than the in-use and operational carbon, which dominates. And outcomes, how the asset is used, is much more important than what it is. So if I build a new bridge or I design a new bridge, I'm going to ask myself, well, what is it? Is it a new bridge to a new airport or something, in which case it's probably not very, very sort of responsible. But if it's a new bridge that allows an opening up of something which is environmentally responsible, then of course it's good. So what it uses, what it's for, is much more important than what it is. This is a chart, again, you won't be able to read, but the purpose of this is just to show the capital carbon, left-hand column, is tiny by comparison with the in-use carbon, particularly in transport. So the operational carbon and in-use carbon is what matters. And of course, the designer, the bridge designer, has very little control over that. I'm just going to finish very briefly by showing two things. One, I'm working on a family of footbridges in glass and carbon fiber for Network Rail. Which is interesting because on the face of it, is this a carbon responsible thing to do? Obviously, pedestrian bridges and pedestrian and rail travel is good from that point of view. And what's interesting is we're looking currently at whether we can use basalt fiber and using natural foam cores and so on, natural materials as far as possible. But this is a kind of all part of an updating of the railways, which frankly hasn't changed much since 200 years ago, 100 years ago. I'm going to skip on because time is running out. But the cross section is basically very sort of straightforward. The other thing I just want to talk to you about is big bridges, because as you may know, a lot of my work is with very long spans, and so just imagine very long span and multi-span suspension bridges, where they needed can actually be a very positive contribution to a zero carbon economy. You know, if electric vehicles are driving across this and saving people from flying, for example, who knows? I take no credit for this work, but I do want to draw attention to it, because this is work that was done by really largely Helen Fairclough and Matthew Gilbert at University of Sheffield, and they asked me to participate in a small way. This is taken from a publication from the Royal Society a few years ago, and if I could just briefly explain what you're looking at. This is the work that was done to optimize the form under just gravity loading for very long spans. The left-hand column is 1 kilometer spans, the middle one is 2.5 kilometer spans, and the right-hand one, I think, was 5 kilometer. And down at the bottom, you can see what looks like a suspension bridge form. You're just looking at one tower, one sort of span, but centered on a tower of a suspension bridge. And the next one up is a cable stayed bridge. And then you begin to get some slightly odd forms. And leaving aside the practicality side of things and how you'd build such things, the one at the top is the minimum weight, the minimum volume, actually, I should say, the minimum volume that comes out of the optimization algorithm. It looks pretty unlikely sort of thing to build, but that is the minimum. And down at the bottom, if you look at a suspension bridge, which is the kind of thing we would build at those spans, again, you can't read it, but I think, and I can't read it here, but I think the figures are about 40%, 50%, and a 70% increase in the weight. Okay, so we're saying that, you know, the theoretical, albeit unbuildable, is a lot lighter. And this is a really interesting piece of work, which I can recommend to you. And as I say, I take no credit for it. There's another picture sort of saying a similar thing, really. The bottom line is the minimum weight with span increasing across the bottom of the chart, and different structural forms being generated by the software. This is an algorithm that generates the form that would produce the low weight, but you could apply constrictions to the software that makes it go into certain shapes. Anyway, it's really interesting stuff. So I just, you know, this is just one illustration, and here's one particular aspect of it, which is to do with pylon height. And if you let it go, this is now with dead load on its own, you end up with a much taller pylon in a suspension bridge than you would have if that we currently use. If you wanted to go for the minimum weight. And I really don't have time to go into these pictures now, sadly, because my time is up. But this is really interesting work, and I can recommend it to you. This is a bit of work we did with when you add live load, you change the scenario radically. And all of this, I should say, recognizes the fact that, you know, in fact, the aerodynamics and other issues are important, constructability issues. But you know, it does show that, and it would generate forms rather like this, leaving aside the practicalities and the aerodynamic side of things. But these are sort of theoretical forms. If I had more time, I would tell you more about that. But that's the sort of thing one can do to minimize the weight. And if I look at this kind of structure, which is the sort of thing we would do for a multi-span suspension bridge, it's a good 50% heavier than the theoretical minimum. So I just leave you with my question.